So this is one of the good example. Actually, the rest of the story that we are going to talk about will be just extensions of the same story. So we have a little box, and we have something coming in, something going out, something decaying, something settling, something evaporate, whatever. And we will regard those as something coming in, and something going out. And the difference of those in and out will be something inside my system. And if you have mass, if you have volume, then you will have concentration. That's it. And if you have a lake, you will have a whole bunch of same boxes connected together. If you have river, same story. Lake will be just X and Y and Z directions. Mostly river will be just one direction, maybe two directions, dependent on the size of your river or dependent on your interest. So we talked about something coming in through the river, something coming in from the wastewater treatment plant, and something coming in from the air. And we know from the principle of continuity, we have a flow rate, and the question is, what is concentration? So we add all together, and then came with an answer. Okay, so we will talk about those a little bit further. So those are answers. And by the way, we talked about resonance time a little bit last time, but I want to re-emphasize the importance of this story, because when you are dealing with pollutant in your wastewater treatment plant, and many times we are interested in cell residence time. And the cell in here is bacteria that is eating your organic material in your input. And mostly we denote this as X. And many times in conventional treatment, we treat UOD as S, right? And cell residence time in here, we denote mostly this with data. So this is some lifetime of bacteria staying inside your system, because this one needs enough time to eat, just like us, okay? If you have lunch, we need some time. But if you join the military, it's a different story, but mostly we need at least some period of time to eat and digest and do something else. So this is very important for a biological entity. In this story, we are talking about the same stuff. So residence time, this one is defined as when you, well, I think I have it in here. Where are we? By the way. Oh, yeah. Okay. Maybe, since we started, and cell residence time in your activated storage system, let's say. And this data is defined as amount in the system and removed per unit time. So if we express those in the form of equation, and tau or theta can be defined as VC divided by V dc, which is out. And in here, the mass rate of output is outflow and decay and settling, right? So if you write it this way, this is your cell residence time or residence time of your seed, okay? And by the way, but we mostly know that residence time water is just V divided by Q, okay? And flow rate for the water, we don't talk about their decay. We don't talk about their settling because it's raw water, just flowing water. In this case, we have no K, no Vs. So K is 0, V is 0 for water itself. For concentration, it has K, it has V, right? The difference material. And so in this case, we can say K and V was actually regarded as zeros. So that's why we have V divided by Q. On the other hand, we do not have, if we had K0, V0, then whole things are 0, right? And this is true for pure water, okay? But we are now talking about the pollutant C. C has K, C has V, because it decays, it can settle, okay? So that's why we carry this one, so we have to consider that part in your calculation. All right. So, well, my lecture usually is repeated. So if you understood in the first time, and some students may think this is very much bored because you're tired of listening to the same old story again and again. Anyway, so I want to take a look at those differences about residence time of water and residence time of pollutant. Very much important. Very much important. Let's say, when we are talking about let's say we currently are studying about this in Han River. This is very, very sensitive issue. Okay? And the people in Seoul, actually political people, they are very much interested in, and we are now doing this study, and they, I don't know, in early November, we're going to present our result, and many people will come in, including the newspaper. And well, we tried hard, and I think we will have some interesting result. But in here, anyway, for you, this we want to find out during the course of flow, if we have some problem in here, we want to know why. And cause of this issue will be phosphorus. What's the word? Phosphorus, the pollutant which is. And also some water from the upper stream. And they get mixed. And if we allow enough time for this to grow, then we'll have a problem. Okay? If we do not allow them to stay there for a long time, they will just flush away. So for this biological something, they need time. They need food, they need temperature, they need friends, they need enemy. They don't need enemy, but if they have enemy, which is zooplankton, then they have trouble. Okay? If they if they compete together, they also have trouble. So we have to understand the basic sciences about what's going on to explain this kind of stuff to other people as an expert. Okay? That's our role in our society. Okay. All right. Then temporal. When we say temporal, means temporal is about time. Okay? And it's about time. About space or distance, we say spatial, right? Okay? Not E, it's A. It's about space. Okay? So, when we say temporal and spatial, and we say this, it's about time and about space, 시공간들, right? Temporal and spatial. And we, those are a little bit, what is this? Not really the, well, in every day we don't learn in our textbooks, but every time when you see those kind of stuff, I want you to pay attention and try to memorize it, because these are very commonly used jargons, commonly used terms in a technical word. Okay, so temporal aspect of pollutant reduction. When pollutant is going to be reduced, and we also know how much time is necessary. Okay, and then when they change, and what is the shape of the curve? Is this just a line or the curve or the cycle light, something like that? So we want to know. Once we know the function, it's easy for us to that we can tell. Right. So we now have this kind of equation. So we rearranged our equation and we came up with this. And when you, I believe you all learned how to solve this one in your calculus, right? 수학했죠? 이럴 때? 다 배웠죠? So I don't have to teach, right? Okay. Well, even though you already learned everything, I will just remind you a little bit. Because we also are biological or something, and we are easy to forget, including myself. So, all right. And in here, this is very common setup of differential equation. And when we solve this one, we will get two different types of solution. And if this one is 0, then we can get kind of general solution. If this is not 0, then we need to have some particular type of solution. And in chapter 4, we're going to talk about particular solutions. But in here, but before we go on, then I can talk about how to solve the problem. If this is 0, and actually we know this one already, because we have seen this so many times before. Okay? But if this is not 0, then we need something special. and it's something special. Because if we have something which is function of time, then we are in trouble. We're in trouble. We need to separate the variable, and we need to collect every c this part. We need to collect every d, every t that part. But if that is just intermingled together, and if we cannot really separate them by right hand side and left hand side, no way. We cannot solve it. Okay? In that case, we have two different options, and we can ask our friend who is good for this, and then we'll just find it here. The other part is we can use the power of computer. So we will learn about that. Okay, so this one is called as the lambda right here, it's eigenvalue or characteristic value. So we will talk about those. So this is the shape of the curve that I'm talking about. What if lambda was 0? Then c equals c0 into the 0 times t, which is 0. And the 0th power of real number is going to be 1. In that case, then we have just c0 that is not changed at all, right? That is constant. Okay, and I think we are going to be talking about pretty much similar stuff. In here, we start to have temperature, and let's have a look at the textbook. Let's see. 3.1. 3.3 decay rate, and it says in example 3.1 we determine the steady state concentration for a lake having the following characteristics as volume and temperature, whatever. If the initial concentration is equal to the steady state level 5.97, determine the general solution. Okay. General solution. General solution is what? The general solution is the solution that you get at WT. So this is okay, right? So what? In other words, if you know lambda, what is the function of c, right? Okay. I don't think I need to repeat that. So next one is response time. So we haven't talked about that either, right? And how much percent? This is 5%. This 5, by the way, is similar to F in the alphabet. Phi is Greek, this the small character, right? And 5, right? And if you have let's say 50% of C0, then this one is 0.5 C0. This is half of C0. And then this is the time, and this is the concentration, which is expressed in terms of C over C0. And so obviously initial condition is 1, and when this one becomes half, how much is time required? This is the question. Okay? And by using this relationship, it's easy for us to calculate T phi like this. If this is 50, then we will get this one. If it's 95, then this one. And people often use this kind of result to estimate the T50 or T95. T50 is if you know lambda, and if denominator is 0.693, is then it is T50. And if you have 3, then you have T95. That means 95% of response, 95% of removal. Okay. And also, this is also very important. And now, so far we have been talking about little tank. Also, some flowing in and flowing out. And if we do not have any inflow and outflow, we call that as batch rate. Batch rate. Okay? Batch means just a fish tank. Fish tank, that's it. Buckets, basket. And if you have something coming in and something going out, we call that as completely mixed flow, because it is flowing. CMF vector, or continuously stirred tank rate, CSTR vector, and which is one of the typical types when we do something in wastewater treatment plant. Okay, so once you know these two, and rest of the stuff are, you will understand just extension of those two. Okay, and next two that I'm going to talk about is the plug flow. It's like something is flowing inside a pipe. Okay, and we can regard this as a lake. We can regard this as a river. Okay, but if you think just a little piece of this one, this little box, and if you forget about the rest of the stuff, and this little box is exactly the same as this one, and then next arrow is going to come to the next box, and then next box, and then these are just the connection of many different boxes. That's it. And what's the difference? In here, one side, if you remember, I said in here I don't have a concept of X, concept of a space, distance. In other words, here, 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 everywhere I have the same concentration. Okay? But in here, first box, second box, third box, their concentration will be different. Right? So in this case then, number one, number two, maybe the distance 1, distance 2, distance 3. And now we start to have a concept of a space. Okay? And one is highest concentration, second is a little lower, third lower, 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 lower. So if we think about this kind of box, let's say concentration. In here, this one is this much concentration, this one is this much, this one this much. So concentration will be different dependent on the location of box, or in other words, distance. Right? So we now start to have a little bit different aspect. So this one is basically connection of CSTR. On the other hand, in our real world, if that is the river, and we don't have their physical separation, we just assume they are connected together. In that case, they can exchange material, right, through dispersion. So that is a little bit more like real system. So then is we consider dispersion. Okay? So then is a flow with dispersion. So it's called as PFD. And this one is called as PF. Where is PF? Okay? 맞아요. Okay, this is, so I want you to memorize the type of reactor, CMF or CSTR. Maybe I will do CMF more often and PF. CMF, PF, those are the most two different important reactors. And this is just another extension, PFD. And there is a model, river model that I made a long time ago. And I am trying to resurrect this one now, and that is the abbreviation of that is the model, name of the model that I made. And actually, I connected CMF reactor and PF reactor together so that I can model our river. Because for the river, and we can regard it as a plug flow or plug flow with dispersion. But sometimes, if you have a reservoir or the weir or some place, water is just stay there, then we can regard it as effective. In that case, we can a little bit have different setup and then do something about it. Okay, so we talked about advection, which is about velocity or movement of the water, and we talked about dispersion, which is the movement of pollutant dependent on because of concentration difference. It's just like temperature different. If you have different temperature and the higher energy is going to move to the lower part, eventually they are going to be the same. And same story here. We talked about that. And for example, if you have a little membrane that can allow dispersion, if you have two different lakes that is connected together, actually this membrane is kind of imaginary stuff. And once we know concentration, which is C1, 1, C2, 1.5, and if you know area, and then if you know the distance between those two, and if you know a dispersion coefficient, right, like that, and we define the flux due to dispersion is like this, and actually dc is something like delta c, which is difference of those two, and dx is the difference of those two centroid, and then we use what is this, 1 kilo, which is a little bit big, but so this is the key right here, and this is 25 something is the dispersion coefficient, and to express this in the form of mass per time, we multiply this by A, because this one is, if without A, this was defined as mass per area per time. So if you multiply this with area, then we'll have mass per time, right? So we have a mass per time right there. This one is a little bit too much exaggerated, but this is the concept about the movement of material through dispersion. Now my question is, and this one is 1.0, this is 0.5, just like here. What is the direction of movement from C1 to C2? And if we define this one is the plus direction, and the mass per time must be plus, right? And we used 0.5 and 1.0, and then this 0.5 is the x2, concentration x2, and this is x1. So we usually subtract x2, x1, x2 minus x1 is we usually using. So we have minus sign here. I want to also remember that. Okay. So again, I showed this to you a long time ago. And we have a basic assumption which is coming in, coming out, and reaction, and then it's going to be accumulated. If we express those in the form of equation, it's going to be like this. In here, if you, in here, as I said, we don't see any x in our equation. So there's no distance above, because inside the tank, everywhere is the same. You don't have to worry about the place. So in here we have two different equations. One is continuity, and the other is mass balance of pollutant. Well, actually, those two are both of them are actually mass balance. This is mass balance of water, and this is mass balance of the pollutant. In here, this one simply has no K and no V, and because we are now talking about this concentrated water is the density. We regard that as just one, and in here we don't care. Even though dependent on the temperature and pressure, that density would be changing. But in here, we will just assume my density is going to be just one for a while. We want to make our life easier. Okay? So, but we call that, well, actually, people in civil engineering, they want to call this as continuity equation, but actually, this is just mass balance equation of water. This is mass balance of my C, right? So, and I have mass in and mass out, something going out, and then I have, when we talk about mass balance, we will say fluidicity. As I said many times before, that came from dm/dt, right? Not just the fluidicity. So this one is like that, and then now it's very easy for us to set up mass balance equation. Now, flow reactor. I said this reactor is the connection of completely limited flow system. So I will just go somewhere in the middle and then just cut that piece and set up mass balance equation and make it general. Okay? So I have a place X, and I have X plus delta X. And I will assume something coming in this side will be QC X. And something going out is QC X plus delta X. Right? In this small piece of the box, I will still have some decay. And I will just define this volume delta V, which is A will be the area of this river, and actually my river is going to be like this. Okay, and I have A here. I have a delta X. This is X. This is X plus delta X. So my volume in here, delta V, is A times delta X, right? So I'm talking about the volume, which is made of this little piece of the toast, bread, whatever, sandwich. So I have something coming in, something going out, something is up here through decay. Okay, and I can divide everything by my delta V, and I'll jump a little bit here, and let's see. me just write this way. And AUCX plus delta X, and minus KC delta V, which is A times delta X. If you can, so I will just divide everything by A delta X, right? And we know my Q is area times velocity, right? So which is AU. I will assume my QX and QX plus delta X will be the same, because nothing happened between there. Using the principle of continuity, my QX will be the same as QX plus delta X. In this case, I have same A and same U then so I can cancel everything like that. Right? So I will come up with the equation like this. And if you, in real world, the velocity in here, the velocity there may change, because of energy loss and something like that. Because if you have a slope like this, and the velocity from here to here will be different, because velocity here will be a lot faster because of energy, the gravity force. But at this time, also we want to make our life simpler, so let's assume those are the same. Okay? So then we can take those out. And then dx equals u. Actually, I want to flip it over, because if we just no, I can't do that. It's going to be like this. If we're in here, we apply the definition of differentiation. Okay, if you change this one is u and c x plus delta x, u c x and delta x, and if we send my delta x to 0, then by definition of differentiation, this is going to be u is going to be the constant and dc dx. But in here, if we this is a t, right? Since we have two different independent variables, one is t, the other x. In this case, we call that as partial differential equation. If you have one independent variable, that's we call ordinary differential equation. Okay, this is if one independent but if you have this one like this, and then this is a partial differential equation, and in this case we use different expression. You may not like this, but you have to like this. But only difference here, there's nothing, no difference at all, no difference at all. But we're just this is kind of our agreement. We just agreed to express things like this. If you don't know t, well, actually c is my unknown, but if you vary t, you will have different c. If you vary x, you will have different c. So x and t are independent variables for you. If you have more than one independent variable, what is independent? And if you have x and y, and if you have curve like this is independent, this is dependent, right? Dependent means it just have to follow its rule. It just have, it's passive. It's passive. So this is my equation. I want you to be happy because you were able to drive this equation. But not happy part maybe we have to solve this one. But for this class, just for you, I'm not gonna talk about partial differential equation, and even though it's gonna be not gonna be too much difficult, and we can use Laplace or Fourier transform, things like that. But we can do it some other class. So in here, we came up with the governing equation for a PF reactor. And this one can be used for any time and for any distance, location. So this one is kind of like your morning bread to make your toast or sandwich, whatever. So I call that a sandwich theory. And sandwich is the actually last name of somebody who really like to poker. He doesn't have enough time to eat, so he developed a sandwich so he can save time. That's the story. But in here, he contributed to the world of one-part modeling, at least in the end. All right. So this is going to be your homework. Okay. Listen carefully. I want to remove my pollutant by 90%. So this is my final concentration. Okay? I have first order reaction and K has a low base. This is a common model that has 10, base 10. Steady state. Steady state means my dCdt will be 0. And if you have your unknown, this is what we have here. If you have steady state, then you have this part 0, right? So this is very easy to solve. And then, actually this is the answer. This is the answer. If you have CMF reactor, your volume will be this much to reach this result. If you have PF, and if you can follow this one, and you will need this much volume. So between this and that, this one is 9 times bigger. So the question is, which one do you like better? Obviously, I like a smaller one to get the same result, right? So this is mathematical stuff, but in physically, so we in the chemical reactor design, and this is very useful, right? So I can save my space 9 times to get the same result, and which is very important because you will save your money and save your space and save your effort, everything. So to know what's going on, to understand what's going on before you do something, that's very much important. So in here, to calculate V, this is piece of cake, right? And to calculate PF, I had round C round D, which is 0, and then I could rearrange this one. And in here, so if you can follow this one, this is not really difficult, but anyway, I will let you do during your homework. And let me go back to this equation right here, and steady state. Then this is 0, then U dC dx equals K times C. Since I have one independent variable, I did not use round, I use D. There is no problem if you want to use round, you can use it, but this is a general way that the used. So if we go on, and we can have things like this, and if we solve this one, and we will have equation like this. I want you to compare this one with that one. What's the difference? I used T. In here I have, when we are in the water jar box, in here we have no concept about X, right? So I have only T. Depending on my time, my concentration will get lower and lower and lower and lower. But in here I have concept about X. What is this? This is something about this, right? This direction, as I go on, I have a lower, 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 lower. So this is about time. This is about X. Even though the shape of the function is exactly the same, we are now talking about totally different dimensions. One is T, the other is X, right? And by the way, I will make you a little bit confused. Let's think about C equals C0 e to the minus kt and C0 e to the minus k over like this. And T, X, U, and there are something that we can talk about. What's the definition of velocity? Right? This is, let's say, my definition of velocity is distance over time. And I have say stuff here. If you switch this two like that. But, so in other words, in here, I can use the concept of the time, but in this case, if you are talking about steady state time, this is the time need to reach at X. It's not the time, it's not clock time, okay? And if you have a constant velocity, in this case, I use T star. This is no more time. When I need to say about required time to reach to a certain space, I will use T star. Well, actually, but those are the same. They can, well, let's take the minutes together. But as long as you understand what's going on, and it doesn't really matter. Maybe I don't need to talk about this, but sometimes, and I myself was very much confused about this, so I am sure among at least one or two of us may have the same problem. Okay, so solve this one, and you